Okay, so let's start our today's lecture. That what where we end our lecture of the Bose Hubbard model. That how do I tackle the Bose Hubbard model in strong coupling regime in the field theoretic way? So I end up by introducing that why and when and how we can use that Howard-Stratonovich transformation, where it is uh, just helps us to decouple off diagonal term, that is that hopping strength, which is the off diagonal thing in this Bose Hubbard model. So it is the case. So let's start by giving a title of Bose Hubbard model. Okay, so now in this case, so I just writing on by saying that Howard Stratonovich transformation. So when we use this Hubbard-Stratonovich transformation at the strong coupling limit, that the strong coupling which is that T is much less than U. So, so in this case, what we do that as the hopping strength is much lesser than the on-site interaction, so we can handle this strong coupling phenomena or the Howard-Stratonovich transformation by doing some perturbative expansion. So we just create a tiny or the small hopping strength and just increase it perturbatively, and in this perturbative expansion we can find some the term involving the local coupling and so on. So how do I introduce how do I do this Howard-Stratonovich transformation? That so first I just say it's a step one. So first step, you have to introduce a auxiliary field. So basically auxiliary field is nothing but a source term which creates a source term, and in this auxiliary field is some way of a mathematical technique that introducing a auxiliary field in the original field, then just integrate it over the auxiliary field and you get back your result in terms of the ordinary field or your actual field, I guess. Okay, so just by introduce, oh sorry, so introduce an auxiliary field. So it's basically step one in this approach, and this field may be written in notation that is psi. The psi I, the I is basically the lattice index and which belongs to the complex plane or the complex number. So basically this field is a complex field. So now our partition function, the z, is basically in terms of the d phi, which is our original field, as phi star, phi, psi star, psi. So as this in the by the introduction of this auxiliary field, our main Hamiltonian of the system just coupled with this auxiliary field, and it makes something the functional of the original or the actual bosonic field and also this auxiliary field. So where so in the beginning I just uh, carefully give you some attentive note that this auxiliary field basically one kind of a mean field of this of your problem. So mean field order parameter of your problem. So it is basically in so Hubbard Session transformation is more like similar of mean field theory. So okay, so after introducing this auxiliary field psi, so our action is basically uh, something action of the local field of function of phi. Then you just identify that another action would be functional of psi, and another would be the coupling between phi and psi. So it's a mixed term. So it just mix you with phi and psi and creates a source term, and that source term creates some propagation of the vertex and something in the field theory language. So that is the case. So if I just write this explicitly, so your phi would be something integral 0 to beta d tau sum over I phi I star delta tau phi I. So it's basically your canonical momenta minus chemical potential times phi I square and plus u by 2 phi I4. So this action, how it arrived in our system or in this path integral, so I already mentioned in the last lecture, so you just take it. So now the main thing of the introduction of auxiliary field by doing a Haber-Stegner transformation. So what how it is decoupled, that your this S of psi would basically decouple your hopping term, so which is the off diagonal of the Hamiltonian. So how it is decoupled, so it couples in such a way that it just connects between the auxiliary field. So basically it should be 0 to beta and ij. So not necessarily it's giving the nearest neighbor thing, just ij psi I star. Now you just introduce hopping matrix, the T inverse of ij. So basically it's inverse propagator and psi j. And the last term, which is coupled with the original or the actual field phi and with the psi, which is the auxiliary field, then your term would be look like that 0 to beta d tau sum over I phi I star psi I plus phi I psi I star. So this is the expression, the mathematical expression of explicit expression of the individual action, which involved the original field phi and then the auxiliary field psi, and how it is coupled between phi and psi. So then you just get all the calculation, and now what we our task, that's the which plays the explicit and the fundamental role, that is why where the Howard-Sachs transformation is taken care, that here that this hopping inverse hopping matrix, that's a T inverse, that basically connect between that side, the auxiliary field. But here I just decouple that in terms of this phi. So I just solve the phi because I want the result in terms of phi, because that's our original field, and then just we just integrate over these shies up or integrate over this auxiliary field, and we get the result in terms of phi. So this is the technique that we could do and decouple that hopping of the off diagonal term with the original field. So okay. Uh, so I think I erase all this part. So basically, where I have denoted that T inverse is this T inverse is basically inverse of the hopping matrix, and it is suggested that and implement the Tij is basically a T if and only if I and j are the nearest neighbor or 0 otherwise. So it is our constraints, and for if in the Bose Hubbard model. So now we have integrate simply and rewritten this partition function of z and integrating over the auxiliary field. So basically integrating over the auxiliary field, we obtain that the original action basically. So we if I integrate over this auxiliary field, then we just obtain this is phi star phi, and which is something s0 of phi, which comes from the diagonal term, and another term that 0 to beta d tau sum over ij, that phi I star tij phi j. So this is the thing. So that doesn't need to nearest neighbor thing. So this tij and phi ij is basically, it recalls us the concept of the inverse propagator. So when we write this action in terms of the auxiliary field, then we just see that this Tij is getting inverted, or the inverse of this Tij. So basically it's kind of some inverse propagator of the theory. Okay, so so here what to do here. So basically we just we just use, so we just use the rules of Gaussian integral, or the Gaussian integral. So what does it mean, the Gaussian integral? So it's basically the rules of making the square, or the completing the square. So in this the quadratic order. So basically the physicists do lots of Gaussian integral, and they are expert to solve something Gaussian integral. So as it is the quadratic order, so we have to complete the square and just do as the rules of the quadratic integral. So this is the basically the step 1. So now after that, how do I find the local correlator and so on? So that should be embedded in step 2, 3 and 4, I guess. So I just defining step to understand all the thing very clearly, that now step 2. So what is the step 2? So we take just trace over or the integrating over the original bosonic field. So we take the trace over the original bosonic field. So the action of the original bosonic field, that after integrating over this part, so we just find that psi star and psi in terms of the new field only basically. So as we just traced over the original bosonic field, so we just left with something in terms of the new field, I guess, or the introduced field, or you may term as something auxiliary field. So what should be your z? That the path integral of the functional integral of psi star and psi, that a to the is 0 of psi, and the rest of the integral of the original bosonic field, that phi star phi a to the power minus is 0 of phi, and minus or maybe a to the power minus of is phi and psi. This is a coupling term basically. So what would give you? So this term would give you something local correlator. So that is basically Z0, which is the local partition function, and the correlator that it just connect between phi and psi. So it should be taking as something average of this part in the local limit. So this is the case, and these Z0 are basically the functional integral of phi star and phi with something e to the power minus s0 of phi. So this is the case. So and how we would solve this part. Okay. So and what we just guess that this e to the power of minus s phi psi, this coupling term, will depend after integrating over. So it will depend only psi star and psi, since we just integrated over with phi, which is the original bosonic field. So this coupling term would ended up its uh, surviving or the survival in terms of this auxiliary field. So that's the goal. And if I erase this part, so what we left here, that your z, this partition function would be z0, that integral, the functional integral of psi star and psi's, and you just taking term that is at local limit of phi plus 0 of, or maybe I just is prime something psi, since that this where your s0 of phi are basically 0 to beta d tau, that I I'm sorry, just I integrate out this phi, so it would give me psi, and another from the coupling term it would get that psi prime. So this is local of psi, and sorry, I messed it up. Okay, so it would give you that psi I star T inverse of ij psi j, I think. Right. And what would be that S prime? So S prime of psi. It is very interesting that that is the log of that exponential of this coupling term, which is phi and psi, at the local limit. So it's a zero. What would be if you take exponentiate this e to the power minus s psi prime, then it basically something the average of something is phi psi at 0, and which would give you something some minus log exponential of that the performing the integral 0 to beta sum over I, this coupling term phi I star psi j, or maybe psi I because it's coupling with in diagonal entries, plus phi I psi I star. So I think it's a good track. It's a 0. Okay, so what do you get that if it's something that your the original bosonic field, then you in terms of this operator basis that you'd ended up your result if it's a time dependent of the imaginary time dependent thing, that you would get something average of time ordered thing of the action, this exponential of something minus beta 0 to beta. So what you have here, that psi I, just replace this phi I star and the phi I in terms of bi dagger, bi dagger of tau plus bi psi I star, and it's a tau. So just I making operator is dependent on the time imaginary time. So it is the basic expression in the written. So in the last step, we just re-express this average over the bosonic field, which is the phi I, as an operator average. So I just express this part as a bosonic average. So I just use the upper thing. So today's class is very much technical and something computational, mathematical class. Here there is lots of concepts and the conceptual analysis, how we build and how to solve, why to solve, when we can solve, or when we can use this technique, that is discussed in the previous two lectures. So here what is the case is basically the last step, just we just re-express the average. So basically re-expressed the average. So average in terms of bosonic operator, terms, oh I missed the spelling, terms of bosonic operator. So it is the case. So as we can do this part, so I just b dagger tau, just it's some imaginary time tau. So I just use some unitarity or preserve this unitarity with the time evolution, that something e to the power h0 of tau bi dagger and e to the power minus h0 of tau. I just do this thing. So as the operator is time dependent, that then I can involve some time evolution operator and just do all the basic needful thing that I just express as the unitary operator. That I just sandwich this unitary operator in this bosonic operator, the time dependent operator, and just taking the average with the time ordered basis. Okay, so that is a very trivial thing, I guess. So this is the thing I just going to do. So just average term is going to re-expressed with some in terms of the bosonic operator, which is the time dependent, and just making this time evolution with the imaginary time and just give the result or take the result you desired thing. So that is the case. So in this time ordering operators, as you know, that time ordering operator is basically if an operator A, which is happens in tau 1, and another operator is B in terms time 2, then your basically would be some A tau 1 B tau 2 when tau 1 is greater than tau 2, greater than equal to tau 2, and basically B tau 2 is A tau 1 if tau 1 is less than tau 2. So it is the definition of the time ordered or the time ordering of the operator which is involved with time. And what we have, that this whatever in this average in the local limit is 0 is basically deals with that the local Hamiltonian. So local Hamiltonian means that all the boson sits in the lattice. So there is no hopping, there is no correlation with the other thing. So there is no off diagonal term in this Hamiltonian. I want to mean that this average of this 0, so you just taking an average in the local limit. So local limit means when the hopping is basically 0. So your thing would be something h naught, so it deals with something h naught. I just recall you that that should be u by 2 ni times ni minus 1 and another mu ni. It's ni's are the operator, and if this is the operator of h, then you could expect for the eigenvalues is in terms of n, and that the eigenvalues are basically in the diagonal entries, comes from the diagonal entries. So now I just giving you a hint of the step 3. So what is the step 3? Basically this step 3 tells you the expansion of this h I prime. What we have written there is a logarithm thing, and just you as we increase perturbatively the small hopping strength, so we can just expand by means of the Taylor series or something else, and up to the desired orders phi. So as you do the large power or the large order, you definitely get some accurate result towards that leads you towards the accuracy. So what would be your expansion? That then should be this ln. So first term would be 1. So if you expand that thing, and then you get something the half time ordered 0 to beta d tau and sum over I psi I tau bi dagger of tau, and you get some Hermitian conjugate of it, uh, and it would basically some time ordered square because it's something expansion, and that should take an average up in the local limit. And if you want to get some quadratic term, quartic term, so that give you 1 by 4 factorial time ordered integral 0 to beta, that is d tau sum over I psi I tau bi dagger of tau plus Hermitian conjugate whole to the 4 and taking average at the local limit. So this is your expansion, and the other term is so on. So we would not interested to do further beyond because it's our desired order. So I just get up to the second term. Okay, so it's a basic trivial basically. I guess you would do. Okay, so if I just erase, so now if I just expand it, these squares and quadratic order, then what we have that that should equal minus of half. If I expand the squares and all that, then it would give you minus half time ordered integral 0 to tau 0 to beta of tau, so integral over tau I psi I tau bi dagger of tau plus Hermitian conjugate, and that could be a square because if you just expand it in this term you get something squared term and this squared term of half and another 1/4, and that gives you something minus half. So that's the basic algebra. So and another term would give you something minus 1 by 4 factorial plus time order tau, and simply that's the same thing 0 to beta psi I tau bi dagger of tau plus Hermitian conjugate times 4, so local limit, and if I close this average limit, and another term would you just find out is the 1 by 8 is a cross term. That should be is time ordered 0 to beta d tau I psi I tau bi dagger of tau plus Hermitian conjugate some square of the part and this average square and so on. So this is our expansion. So if I erase this lower part of the board, I think just I can write the furthermore this form. That is basically the quadratic order of psi and the quatric order of psi. and so on. So this is the case. So evolution of this quadratic term, so what would be? Mm, So we are interested in the quadratic term. So basically, quadratic action. When you form the quadratic action, then that quadratic term basically leads you into a Gaussian type of integral, and where you just make some completing the square, you just evaluate your desired result. So our desired goal that to look into to the quadratic order. So I just write this part. Okay, so I just so evaluation of the quadratic terms. Quadratic term that is I of 2, that is of prime. Okay, so this is prime of the quadratic order psi, that would be basically your 0 to beta d tau 1, 0 to beta d tau 2, and what you have, that's ij psi I star of tau 1 and psi j. So after some evaluation, that's tau 2, and the average part is basically time ordered bi dagger tau 1 and bi tau 2. So basically this average in the local limit gives you the correlator basically. So how it is correlate between I and j, and taking that uh, tau 1 is basically tau 1 and tau prime is basically tau 1 minus tau 2. What do we get here from this? So we get something, so minus of d tau minus beta 2 plus beta, just change the limit, that's d tau prime. Then what you find here, that the psi I star tau and remaining psi I of tau minus del tau of psi I tau with something tau prime plus the half del tau, the second order derivative, I guess. So of psi I tau with some tau prime square, finished it up, and this correlator is basically look like bi dagger of tau prime bi of 0. So what we do, as we just uh, replace this or the rename this part, then what you have, that this tau 2 are basically tau 1 minus, so tau minus tau prime. So this psi j, this part is basically the argument or the function of this psi j are becoming some tau minus tau prime, and this tau 1 is basically replaced with something tau. And what we did here, that this psi j minus psi j of tau minus tau prime, that I just expand in terms of the Taylor expansion. So I just expand by using the Taylor expansion. So by doing this Taylor expansion, what we get that this psi j term, this psi I tau is the first term, and then del tau the first derivative, and in the near this tau prime, and then the second derivative, and so on. So basically it goes, but I truncate up to the second term. So what it gives me, that I just named it. So I just explain it little bit after a little bit time, that I just named here this psi is basically 0 to beta d tau I something k1 some coefficient. I just explain why this coefficient is very much important. I psi I square plus I square. So I just uh, summarize the second quadratic order action in terms of k1, k2 and g0. So I just tell you after some time that what we why we just do this k1, k2 and g0 in terms is this coefficient basically something the perturbative expansion. So as it's perturbatively expanded, so basically the energy eigenvalue of the perturbation, maybe the second order perturbation, gives you something kind of result. So we just do it after few time. So first thing first, that I just rewrite this in form of k1, k2 and the g0, which is some terms of the coefficient. And if I define, so I just rewrite it again, that say what we have, d tau some k1 of psi I star del tau psi I plus something k2 del tau. So it's a complete derivative actually. And another part, this basically gives you the eigenvalue of the perturbative expansion of the energy eigenvalue. So this is the case. So and also this will give you something some. Okay, so this what this g0 means basically. So this g0 is basically minus beta 2 plus beta this d tau time ordered bi dagger tau of bi of 0. So this correlator basically, and the Fourier transform, that's the Fourier transform of this single particle Green's function of this g0 is give you that the single particle Green's function. Which basically is something g of the local limit 0 tau 1 minus tau 2, and which is basically something Fourier zero frequency in the zero frequency limit. So so in 0 frequency limit. So in the frequency space, it would gives you much more convenient thing. Bi dagger. Oh, I'm sorry, I just made up a mistake here. So it's a bi dagger. So bi of tau, bi dagger of 0, and so on. This k1 is basically minus beta 2 plus beta d tau, that time ordered. But there is a something okay, so I just write it bi of tau, bi dagger of 0 in the local limit, and another tau would be there because I just make some Taylor expansion of this thing. And last term, that's the k2, that should be that half minus beta 2 plus beta d tau time ordered bi tau bi dagger of 0 of tau square. So it basically gives in the how this k1 and k2 are basically defines the tip of the Mott lobe and so on. So I will explain that in a minute, but it's something very trivial. You can think of this a technical and the mathematical expression that we just rearrange that action in terms of something k1, k2 and k3, and that k1, k2, k3, what maybe something g0, k1 and k2, the coefficients of the quadratic action, that basically depends on this correlator, and which whose Fourier transform is basically gives you some single particle Green's function in the imaginary time limit. So as imaginary time is concerned, so basically it's a time ordering is basically the essential thing, that how these fields are correlate to another field and each other. So basically this would be the scenario, and we have to find, this is then the trivial consequences of this Bose Hubbard model. So we if I want to know that consequences, so then we have to determine this correlator first at the local limit. So wherever I just putting this 0 sign, just you just think of this local limit, that means only the diagonal terms of the Hamiltonian are involved. Okay, so I just evaluate how this term would be. Okay, so then I just give you the essence of k1, k2 and the k0, and for the information I just reveal the secret that these g0 are basically the second order perturbation eigenvalue. So second order eigenvalue of the perturbation theory. If you just taking a Hamiltonian of the mean field in the mean field level, then you just add some hopping, and you just expand this hopping perturbative way, and the second order perturbation, the eigenvalue of the perturbation theory of the Bose Hubbard model is essentially gives you the G0, and whatever this G0 turns out, that is basically the energy eigenvalue of the perturbation theory if you solve that in the mean field theory or the through the mean field theory. So in the field theoric way, where we just introduce the path integral formalism and all that, that path integral formalism does not uh, which basically differs you with the fact of the mean field theory. It's basically the same way. That's the different perspective of seeing the Bose Hubbard model or the tackle the Bose Hubbard model in the strong coupling regime. So in the Taylor expansion, you could notice that this perturbation that happens as the perturbation theory tells about in the Hamiltonian level, and the field level where we introduce some auxiliary field and all that, and that just drives me into this same story of the mean field theory. So basically these size as auxiliary fields are basically mean field. So it's a analogous to mean field. So that's it. Okay, so let's do. So this would easily calculate that this if you take the number basis. So how do you calculate this g0? That's the Green's function, the local limit. So single particle Green's function, that tau1 minus tau2, and that should gives you some minus time ordered bi of tau, bi dagger of 0 at the local limit if tau is basically greater than equal to or 0 and so on. So you can take this tau1, and I think it's a tau2, it's maybe a trivial thing. So tau1 is greater equal to tau2, and another thing would give you that time ordered bi. So I can write this thing again, this tau1 minus tau2 bi of 0, and so local limit. Okay, so if you do this tau1 greater than equal tau2 in this time ordered scenario, then you just have this Green's function, so tau1 minus tau2, that gives you basically bi of tau1 and bi dagger of tau2, and which gives you basically the trace something, some z and trace, or maybe I just use the Fock basis n and e to the power minus beta, the eigen value of this Hamiltonian epsilon n, and is n squeezed over b tau1 and b tau2 of dagger and the n. So this is the case. So I guess you just take this average. It's very easy that you first do this time independent sector, then you would get something e to the power e to the power h of tau1 and to minus h of tau1. Just take a unitary operator and make this operator time independent, and you know the how the creation and annihilation operator are operated in a Fock basis. So what you turns out that if you just do this operator operates, that's b dagger and b either, and make it some time independent, and then operate this b dagger and b over n and the e to the power exponential of h, that's the unitary operator over the Fock basis, then you just turn out the result that minus of z0, so partition function in the local limit, that turns out some n plus 1 is the eigenvalue, and you get minus beta epsilon n. So exponential of tau1 minus tau2 of epsilon plus of n. So it's basically particle excitation. So epsilon plus of n is basically epsilon n plus 1 minus epsilon n. So it's basically the particle excitation. So you just add a particle. So as the creation operator is here and annihilation operator is here. So if you operate over this n, then you just get it, the one particle just add to the bosonic lattice site. So you just ended up your result with some particle excitation. Okay. So what would be the result in if tau1 less tau 2, the result would be similar, that your Green's function at the local limit would drives you in that z0 n times e to the power minus beta epsilon n e to the power minus tau 1 minus tau 2, I guess. Okay, so it doesn't need tau 1 minus tau 2 and width of epsilon minus of n. So this epsilon minus, it's some whole excitation. So it's basically epsilon n minus 1. So this epsilon minus of n is basically epsilon of n minus 1 minus epsilon. So this is the case. So it's a whole excitation. So if you just take this, or may you just try to evaluate this Green's function in the local limit, just you get some eigenvalue that involves the particle excitation and particle whole excitation. So one just it creates a particle and another just annihilate a particle by this correlator. So you can think of this correlator basically the simultaneous hopping in between I and j. So basically this Green's function is basically correlate the thing. So as if this in the local limit, it may be just it's a Green's function maybe. And another thing would happen that if it is a I and j, one particle just goes I to j and another particle come j to I, and these occur simultaneously. So you just sit in the Mott limit, there is no density violation by this hopping, or it preserves the translation symmetry, and also the hopping processes are involved here. So this kind of the Green's function, if you approach from the atomic limit and introduce hopping perturbatively, then what would happen that these two kind of processes are basically exist, and the two kind of processes can be dealt with by this Green's function in the atomic limit. Okay, so after that we just introduce hopping and do perturbative expansion of this Green's function and get some uh, dispersion relation, and from the dispersion relation we may have some critical order or the critical exponent. Maybe I would say there is a dynamical exponent of this thing. I hope you just basically feel free to calculate all kind of correlators by taking this formalism. And for the bosonic case, it's very trivial. And if you take this fermionic case, then this time ordered product are basically same. But in the fermionic Green's function, the methods are same, but what you just to do that be in between bi's and then bi sigma and the bi dagger sigma primes are there, and also that would be follows the commutation relation. So that is the game. So just we calculate the Fourier transform because it's a frequency limit if I want to go. So ft Fourier transform in zero frequency limit. So that G0 in the zero frequency limit, that would be minus beta 2 plus beta d tau G0 of tau. So as we find this G0 of tau in these two limits, that you get that m minus beta to 0 d tau e to the power epsilon minus this whole excitation. So I think it's right here, m of tau, and another quantity would be m plus 1 0 to beta d tau, this is a particle excitation m of tau and tau. So this is a Fourier transform which basically connects the frequency space and the imaginary time space. And when you go or end up our result in the frequency space, that would be that frequency is basically conjugate of this imaginary time, and that is basically known as the bosonic Matsuburg frequency. So bosonic Matsuburg frequency would appear if you do in the frequency mode, not in the zero frequency mode. So I just given you example in the zero frequency limit where we just taken the Matsuburg frequency 0. Otherwise, you just ended up your result with something Matsuburg frequency, having a Matsuburg frequency. And if it's a bosonic, then it would take the value something 2 pi n over beta, and if it's a Fermi unit, your Matsuburg frequency takes the value 2 pi n plus 1 times beta. So one is basically even increase and another would takes only the odd increase of the n. So maybe we would say precisely that Matsuburg frequency are 2 pi n by beta, and another is 2n plus 1 pi by beta. So that is the thing. Okay, so in the zero frequency limit, we don't need to bother how the Matsuburg frequencies are behaved. We don't need to take Matsuburg frequencies because we always deals with a zero frequency regime to make this continue to fill the all the space and all the Green's function in the uh, analytical continuation regime. And that analytical continuation leads you that the omega plus I eta and eta is goes to 0 is a retarded Green's function and all that. And I think that this Green's function, the zero frequency limit, would also behave in the same way if you put the Matsuburg frequency. So it does not basically change the description of the Green's function if you take some zero frequency limit or you do not involve zero frequency limit and so on. Okay, so what you would get here after doing this integral, that that should be some minus m over whole excitation of m plus m plus 1 particle excitation of m. So I think I am right. So here what we have, this is some Green's function of the single particle Green's function, the zero frequency limit. And in the Fock basis, I just get some m is a number, there is a number of bosons, the number density that sits in the lattice site, and this creation that whole excitation and the particle excitation gives you if you add some particle or extract some particle from the lattice point and how the Green's function correlate each other. So that is embedded here in way that what is by introducing the imaginary time ordering. So that's the simple case and the trivial matter. So now you can think of this, there is a simple trick to obtain this result, that uh, so the explicit form, as you find out that plus minus of m is gives you basically m times u minus mu, and another is 1 minus m times u minus plus mu. So in terms of the parameter, that is the on-site interaction and the chemical potential, the epsilon plus, it's a particle excitation are mu minus mu, and this part 1 minus mu plus mu. So you just have the energy eigenvalue, that's the epsilon of m, from the local Hamiltonian of the Bose Hubbard model, and then if you just have epsilon m plus 1, just you just calculate the particle and the whole extension, you just get the result very trivially. So it's some bit of a algebra, not a very bit of algebra, it's a very simple algebra. Okay, so as we find that the Green's function and tau 1 and tau 2 regime, then you get that first term in the when it's basically tells you tau 1 is less than tau 2, this portion of the integral, and this portion is integral tells you this greater than equal tau 2. So what we can find that tau of g0 of tau, that g0 of tau already I just encountered and evaluated that average at the local limit is a pi dagger and pi in the time ordered value. So in the findings of k1 and k2, the tau g0 tau that leads you that delta g0 over mu, and tau square g0 for the case of tau is basically del 2 g of 0 del mu 2. So basically this thing is leads you to the coefficient k1, and another this term is leads you to coefficient k2. So now can you just guess that uh, this g0, this k1 and k2s are basically involving the derivative of the chemical potential, the first derivative and the second derivative. And as you know, if you think of this Green's function is basically analogous to your free energy of the Hamiltonian, then the positive or the negative value of the first and the second derivative of with mu, then you just ended up your conclusion that in which regime your system heats the phase transition. So, and which order phase transition, rather we say precisely that if it diverges at the first derivative, then it creates you the something first order phase transition, and at the diverges at the second order regime, then it would give you the second order phase transition. And I hope you would just guess which order phase transition the Bose Hubbard model would exhibit. And the thing is that the evolution of k1 and k2 and some g0, which is the prefactor of the quadratic action, and this thing leads you towards some analysis of the critical theory. It's an amazing thing. So it's the case. I think you would just realize what I try to explain you here. Okay, so okay. So what you get that as your k1 is basically minus beta 2 plus beta d tau, tau of g0 of tau, then it's basically minus del mu of integral d tau g0 of tau. That means it's basically minus del g0 del mu. So if you find the Green's function in the zero frequency limit, you would basically find this k1, and similarly for the k2, as it's half of minus beta 2 plus beta d tau of tau square of g0 tau, then it should be gives you something half of del 2 g0 of del mu 2. So since the solution of the evolution is a quadratic order, that you just think of the quadratic order action is basically deals you some coefficient h 0 to beta and d tau of psi I to the power 4. So this is the interaction term, the on-site interaction term. So now I don't want to do this calculation, the explicit or the thorough calculation of psi I 4, because it's something average of time ordered, something average of the time ordered psi I dagger, psi I dagger, psi I, psi I. So it's not very difficult, but it's tedious, the tedious calculation. So it's giving you so long period. So it's basically the fourth order perturbation basically. And since in the free energy expansion, if you do perturbative or non-perturbative way, so if you have some free energy, you can expand in terms of the second order perturbation and the fourth order perturbation in terms of the value of positive or negativity of A2, or that a coefficient of the second order perturbation term, that leads you to the towards the spontaneous symmetry breaking that breaks some Z2 symmetry. So so it is very useful, the result of this fourth order perturbation theory, but I don't want to do this uh, for that, because it's a tedious calculation and it's gives me a lots of difficulty. So I just write it the expression of H, that m epsilon of m, it gives you some this kind of result, m plus 1 epsilon plus m times m epsilon minus second particle or the whole extension plus m plus 1 plus 2 m and m minus 1 epsilon minus 2 of m epsilon plus 2 of m, so and minus m plus 1 m plus 2 epsilon plus 2 m and epsilon minus 2 of m. So basically this epsilon of 2, and that basically epsilon plus or minus of 2 is basically epsilon m plus minus 2 minus epsilon m. So this is thing. So I guess that could be determined very easily. It's a pure algebra. The technique of finding or the evaluation of the second order or the fourth order term is alike with the second order term, but the mathematics is very tedious. So I think that's it. This is some mechanical thing. Okay, so I think it is the best point to stop today's lecture, and I think the another lecture would be in the next in this series. So in the next lecture, what we try to analyze that exact the critical theory, that how this K1, K2s are basically gives is basically the analogical statement of the expansion of the free energy, and how K1 and K2 are basically behaves, and due to the value of the positive or negative value of K1s and K2s, and how the spontaneous symmetry breaking is basically eventually plays a role in the Bose Hubbard model, where the phase transition occurs in the Mi to SF phase, and so on. So in the next class, I would like to discuss the whole critical theory and the determination or the tackle or of the all the Hubbard model in field theory or the path integral way. That is just you have to obtain the atomic limit Green's function, and all the thing this the perturbatively I just encountered, and all the scenarios are developed in terms of the local Green's function, and so that's it. So local Green's function are very easy thing to find out, and if times permit in the next lecture, then I would discuss that what would be the dispersion relation when the finite hopping is introduced in the local Green's function. So for that, the last lecture of this series, please stay tuned and make you keep your curiosity holds and embark your curiosity to know what how the critical theory would be appear here. So that's the case. Thank you.